Welcome to B.Sc Statistics students. In this class, I explain derivation of rank correlation coefficient for tied ranks. Already I have discussed derivation of Spearman's rank correlation coefficient for untied ranks, that is normal as usual, without ties. If you have ties, then how to calculate rank correlation coefficient formula? What is the derivation part? Sometimes, usually, some number of individuals receives the same rank, which are called, the ranks are said to be tied, which are called tied ranks. The ranks are said to be tied. For example, second, third and fourth, 3 students got same marks, so therefore they have to receive some particular rank which is average of all 3 individuals, 2 plus 3 plus 4 divided by 3, that is the third rank. 2 plus 3 plus 4 divided by 3. So second one, third one and fourth one receives the same rank. These are the 3 individuals, 1, 2, 3 receive same rank, which means the same marks. So therefore same rank. What is the rank? 2 plus 3 plus 4 divided by total number of individuals or 3. Hence it is 4 plus 3, 7 plus 2, 9, 9 by 3 it is 3. Average, you can simply calculate average, that is 3. Third rank for second person, third rank for third person, third rank for fourth person. This is the way you have to give the ranks, that is, which are called tied ranks. Ranks are said to be tied. Okay, this is the case we have to consider, and you have to derive the rank correlation coefficient. What is the formula of rank correlation coefficient? I am quickly coming to the discussion. For example, there are m individuals having the same number of marks, obtained the same number of marks. Then the ranks of m individuals are said to be tied. After some particular k ranks, for example, here the ranks are 1, 2 and so on up to k, and then for example k plus 1, k plus 2 and so on, k plus m, because we are considering the tie for m individuals, which refers 1, 2, 3 and so on m. That is, m individuals got same rank after kth rank. The 1, 2 and so on k, there is no tie, and after that, for example, m individuals receive same marks, hence the ranks are tied, which means they have to receive the same rank, they have to allocate same rank, for which actually the ranks are k plus 1, k plus 2 and so on k plus m, which are tied. Clear? Is it clear? The ranks are. This is our discussion. This is one set of ranks. After that we have some number of ranks. Depends on how many number of individuals. Okay, right? If there are n individuals, out of which m individuals are getting same number of marks, and them ranks are tied, so that m ranks are tied. Clear? In which case, in this particular case, you have to derive the rank correlation coefficient formula. As usual, I am considering the Spearman's rank correlation coefficient formula. Spearman's rho, rank correlation coefficient formula. Rho is equivalent to B. It is going to be considered as the formula of covariance of x comma y divided by sigma x sigma y. Firstly, what is covariance of x comma y? It is equivalent to be 1 by n summation I is equal to 1 to n xi minus x bar into yi minus y bar divided by sigma x sigma y, the square root of standard deviations, hence 1 by n summation I is equal to 1 to n xi minus x bar whole square into again 1 by n summation I is equal to 1 to n yi minus y bar whole square. Clear? This is what the usual formula by cancelling 1 by n. By cancelling 1 by n, the remaining formula, that is rho is equivalent to be summation I is equal to 1 to n xi minus x bar into yi minus y bar divided by square root of summation I is equal to 1 to n xi minus x bar whole square into summation I is equal to 1 to n yi minus y bar the whole square. Clear? If you consider, that is, let xi minus x bar is equal to ui and yi minus y bar is equal to vi, then the formula now it becomes rho is equivalent to be, this is summation ui vi, I is equal to 1 to n ui vi. You please remember that summation always refers I is equal to 1 to n always here in this particular, because n individuals you have, so that is the reason why it is always summation I is equal to 1 to n for ui and vi, and summation I is equal to 1 to n ui square into summation I is equal to 1 to n vi square. This is ui square, this is vi square, summation ui square, summation vi square. Now what you have to see that in which x bar, y bar, there are three particular terminology you have. I will tell you what are the changes in these quantities. That is very important. These quantities means the formula x bar. You refer this particular entire formula x bar, y bar and summation xi minus x bar whole square, summation yi minus y bar whole square, and summation xi minus x bar into yi minus y bar. So these are the values you have to see what would be the change if the some ranks are tied. If some ranks are tied, and what will be the changes in these formulas, in these quantities. Now first of all, x bar and y bar, if you consider xi and yi takes the values 1, 2 and so on n, because the ranks, please remember, if the ranks are for n individuals, then the formulas of x bar and y bar, all the formulas I am checking the formulas, okay, right. If xi and yi, which are all the values, which are nothing but ranks of the individuals, usually the ranks of individuals for n individuals, the ranks are 1, 2 and so on n, right. Then x bar is nothing but, and y bar is also is equivalent to be n plus 1 by 2, already we have calculated. It is nothing but sum of the ranks for n individuals. X bar is nothing but summation x by n. I should not, I need not explain this. These are the values here. Summation xi, that is summation of 1 plus 2 plus and so on n divided by n. Okay, is nothing but n into n plus 1 by 2 divided by n, that is multiplied by n. So hence it is n plus 1 by 2. So like that y bar is also. So these are the values we have discussed already in the derivation of the Spearman's rank correlation coefficient without ties. Now similarly, just the sigma square x, the formula is n square minus 1 by 12, and sigma square y is also same. Now in which even though tie occurs, x bar and y bar do not change. I will give an example so that you can understand. 1, 2, 3, there are 3 individuals. The ranks are 1, 2, 3. The average is 2. for which, for example, x bar, the average is equal to 2. Right? 1 plus 2 plus 3 divided by 3, it is nothing but 2. For example, all three individuals got same marks, hence there is a tie occurs. There is a tie. So then we have to allocate the rank for 1 plus 2 plus 3 divided by 3, it is equivalent to 2. 2 for all individuals. For first individual 2, second individual 2, third individual also 2. You calculate, this is without ties. The ranks without ties. There are no ties. Ranks were with ties. Then you calculate average here. 2 plus 2 plus 2 divided by 2. The average is also, here also x bar is 2. Therefore, x bar, the mean value do not change even though tie occurs. Even though tie took place, tie is taken place. It do not change. X bar, y bar values do not change even though tie occurs. X bar, y bar values are not going to be affected, changed. Clear? That is one best example I have given here. You please go and study this. Right now, I have to see the changes in the sigma square x and sigma square y and then covariance of xy. So these are the individuals I have to, these are the values I have to see the changes if tie occurs, right? So therefore, now I see the, now I observe the changes in the sigma square x, sigma square y, in which sigma square x, just now I have considered sigma square x is nothing but, it is 1 by n summation I is equal to 1 to n xi minus x bar whole square. Let you consider 1 by n summation I is equal to 1 to n ui square. Xi minus x bar I have considered ui, hence it is ui square. Right? The summation ui square. Now, so what is sigma square x? N square minus 1 by 12. It is equivalent to be 1 by n into summation I is equal to 1 to n ui square. Right? So therefore, it is equivalent to be summation I is equal to 1 to n ui square is equal to, I am taking this on left hand side, so n into n square minus 1 divided by 12. What is this? Summation ui square. Therefore, summation ui square is nothing but, I write in the in a particular format. Summation I is equal to 1 to n ui square is equal to n into n square minus 1 by 12. Similarly, if you consider for the sigma square y, then summation I is equal to 1 to n vi square is also n into n square minus 1 by 12. Why I am deriving these formulas? The variation will be in only the sum of the squares. I will tell you in the same example. I consider the same example here. For example, 1, 2, 3 are the ranks without ties for 3 individuals, and with ties the ranks are 2, 2, 2. If you have tie, then for all 3 individuals 1 plus 2 plus 3 divided by 2, rank for first, second, third individuals are same 2. Now you do the square here, 1 square plus 2 square plus 3 square, sum of the squares. So what I am doing is sum of the squares. There is an example, I am giving only an example. I am observing only the sum of the squares. Remember, sum of the squares. Sum of the squares is nothing but summation xi square, for example. Summation xi square. It is the sum of the squares, in which x bar do not change. X bar, the value is not going to be changed. That's what in the previous example I have clearly explained that the x bar and y bar do not change. Which will be changed? The sum of the squares. I'll prove here. 1 plus 2 plus 3, 1 square plus 2 square plus 3 square. Sum of the squares. 1 for 1, 2, 3 ranks. It is 1, 4 and 9. 1 plus 4 plus 9. It is nothing but 14. Now, 2 square plus 2 square plus 2 square. Sum of the square for tied ranks. It is 4 plus 4 plus 4. It is 12. So, quantity. Now, you see sum of the squares here 14. Sum of the squares here 12. Clear? Is it clear to you? So sum of the squares will be changed. Particularly it is going to be reduced. After ties, that is after allocating tied ranks, the sum of the squares will be reduced. Here 14, it is reduced to 2, the quantity 2. 12, sum of the squares after ties it is 12. So this is what our discussion. The main discussion in the derivation of the Spearman's rank correlation coefficient with ties is nothing but the sum of the squares particularly. Thereafter summation ui vi also, that is covariance. The two particular terms, variance and covariance, are going to be changed. Invariance, particularly sum of the squares, and product summation xi yi. These are the two particular terms are going to be changed. So therefore, now you have to see the change. Okay, right? Before that, I will tell you the change in the summation ui vi as well, for which I am considering. You see, is it clear to you? Summation summation ui square is this, summation vi square is this. Now I calculate summation ui vi as well. You know, to calculate summation ui vi, you have to calculate, you have to consider summation di square. So I am considering summation di square I is equal to 1 to n. Summation di square is nothing but, you know the formula, summation I is equal to 1 to n xi minus yi whole square. You recollect the derivation part of the Spearman's rank correlation coefficient without ties. Summation di square you have to consider here, right? And summation di square xi minus yi whole square, for which I am considering that I am adding and subtracting x bar. Summation xi minus x bar minus of yi minus y bar. X bar, y bar are equal. That is the reason why I am adding subtract. That is minus x bar minus x plus x bar, minus of minus plus x bar. X bar I am taking as y bar. Hope you understand. I am adding and subtracting. Here I write again xi minus x bar minus yi minus x bar. That is minus x bar plus x bar. This x bar I am changing as y bar, right? Whole square. Right? Clear? The whole square. So here subtracted, here added. So xi minus x bar, yi minus y bar. What is xi minus x bar? It is ui. Minus what is yi minus y bar? It is vi whole square. So then by doing the square here, summation ui square plus summation vi square minus 2 summation ui vi, I is equal to 1 to n. Always I refer I is equal to 1 to n and the entire this particular contest, right? So summation ui vi it is required. This is summation di square, I is equal to 1 to n. Now you have to calculate summation ui vi. So therefore summation I is equal to 1 to n ui vi is equivalent to be, you take summation di square right hand side and this one minus of term the left hand side, so it becomes plus and this becomes minus, and divided by 2. So therefore it is 2 multiplied by 2, if you take in the right hand side, divided by 2. 1 by 2 multiplied by summation I is equal to 1 to n ui square plus summation I is equal to 1 to n vi square minus summation I is equal to 1 to n di square. Is it right? Okay. Have you understand this? This is what summation ui vi is equal to 1 by 2 into summation ui square plus summation vi square minus summation di square. Okay, let you consider this is one such particular equation. Alright, equation 3 let you consider. These are the two particular values 1 and 2. Okay, right. So summation, you see, you refer here summation ui square is this, summation vi square is also same this. Now and summation ui vi is also the terminology, the term in terms of summation ui square, summation vi square, and summation di square. If you see the change in summation ui square and summation vi square, which is enough, and summation di square, which is enough to know the variation in summation ui vi. So these are all the values without ties. Now you have to see the changes with ties. If you have tie, then what would be the changes of the terms summation ui square, summation vi square, and summation ui vi. These are the three particular terms. What would be the changes in these terms? You have to see now. What you have to see? You have to see the changes if tie occurs. You have to see the changes in the terms summation ui square, summation vi square, summation ui vi. That's all. For which already I have explained that x bar and y bar values do not change, and then you have to consider there are two particulars, sum of the squares. What I am considering? Only sum of the squares. I have given an example here, sum of the squares without ties and with ties, sum of the squares. So now I am considering to see the changes in the summation ui square, summation vi square, summation ui vi. Sum of the square terms I am considering. Sum of the squares for untied ranks I am considering s square, that is sum of the squares of untied ranks, that is before getting ties, before giving the tied ranks. These are the sum of the squares I am considering. And s square t, let you consider sum of the squares for tied ranks, after giving ties, the sum of the squares you consider s square t. Sum of the squares before giving the ties, that is untied ranks, the sum of the squares I am considering s square. I see the difference between s square and s square t. That is what my main objective, and so that the formula is going to be derived. Right, clear? Now I consider these two particular parts, s square and s square t. For example, I have already considered that there are there are m individuals who got tie in the ranks. That is, I am considering k plus 1 after k ranks, k plus 2 and so on, k plus m. These ranks are, for example, are tied. M ranks are tied. Now we have to consider s square, sum of the squares without ties, and s square t with ties. Only the change I am considering, not I am considering all the ranks. Only the ranks which got ties. For example, m ranks are there, m individuals are there, and who got tied? The ranks are tied. For those ranks, let us consider without ties, what would be the sum of the squares? That is s square. And with ties, what would be the sum of squares? That is s square t. So first of all, without ties, that is untied, let us consider untied ranks. Sum of the squares for untied ranks, that is s square, which will be simply sum of the squares, that is k plus 1 whole square plus k plus 2 whole square plus and so on plus k plus m whole square. So it is equivalent to be the k square a plus b whole square term. So a square term, k square plus and so on plus k square. How many k squares? M k squares. So m k squares plus b square term, 1 square plus 2 square here and so on plus m square plus 2ab term, 2 into 1 into k, 2k, 2 into k and so on 2 into m into k. That is, we can take a common 2k and multiplied by 1 plus 2 plus and so on plus m. If you take a common 2k, k is always there, that is for in all the terms, and 1 plus 2 plus and so on plus m. So therefore it is m k square plus sum of the squares of the first m natural numbers. It is nothing but m into m plus 1 into 2m plus 1 divided by 6. Clear? Plus 2k into sum of the first m natural numbers, that is m into m plus 1 by 2, m plus 1 by 2. So 2 will get cancelled. So the term here m into k square, this is s square, plus m into m plus 1 into 2m plus 1 divided by 6 plus k into m plus 1. So this is what the one equation I am considering. Equation, let us consider equation 4. Right. Similarly, now I am calculating sum of the squares of the tied ranks. If these individuals are tied, what would be the rank it is going to be given? It is divided by m, k plus 1 plus k plus 2 plus and so on plus k plus m divided by m. That is the rank first of all. So sum of the squares of the ranks, that is k plus 1 plus k plus 2 plus and so on plus k plus m divided by m. This is the rank whole square, plus similarly second individual also, k plus 2th individual, k plus 1th individual rank, k plus 2th individual receive same rank, that is k plus 1 plus k plus 2 plus and so on plus k plus m, k plus m divided by m whole square, plus and so on plus k plus mth individual also receive the same rank, that is k plus 1 plus k plus 2 plus and so on plus k plus m divided by m, the rank of the k plus mth individual whole square. This is the sum of the squares of the m individuals after receiving k, that is k plus 1, k plus 2 and so on k plus m. The average is k plus 1 plus k plus 2 plus k plus m divided by m. If we have a tie for m individuals, the sum of the squares of all the ranks, first ranks at k plus 1th rank, k plus 2th rank and so on k plus mth rank, right? Clear? So now we have to do the sum. You see here divided by m. So here are all terms are same. So therefore you can simply write m into m multiplied by m is equivalent to be, I am writing here. Clear? Right. Is equivalent to be m multiplied by k plus 1 plus k plus 2 plus and so on plus k plus m divided by m whole square. Clear? And in which now simply m multiplied, we can cancel one m. Yes. So after calculating one m, we have only one particular m in the denominator, and then here you see here k plus k plus k. How many k's? M k's. So m into k plus 1 plus 2 plus and so on plus m. Okay, write that down. 1 plus 2 plus and so on plus m whole square divided by m. This particular m I have cancelled, right, with this m square here. So I have cancelled one m is equivalent to be now mk plus 1 plus 2 plus and so on plus m, sum of the first m natural numbers, that is m into m plus 1 divided by 2 whole square divided by m, right? So it is equivalent to be, if you take again m is a common here, so therefore I am taking common m. If you take outside it will be square multiplied by k plus m plus 1 divided by 2 whole square divided by m. Is it clear? Right. So again one particular m will be cancelled. So m multiplied by k plus m plus 1 divided by 2 the whole square. This is the term for s square t. S square t. So therefore it is equivalent to, if you still expand this, and this will be m into k square, a plus b whole square, m into k square plus m into m plus 1 whole square divided by 4, m plus 1 whole square divided by 2 square 4 plus 2ab term, m in 2 into m into k multiplied by m plus 1 divided by 2. So 2 will get cancelled, right? So therefore, here the final term I write in the next page. The final term for s square t, therefore s square t is equivalent to be m into k square plus m into m plus 1 whole square by 4 plus k into m plus 1. So this is the term, right? So therefore, if you consider this is the next equation from, if you observe 4 and 5, if you observe 4 and 5, I show the equation 4, that is s square, this is s square mk square, this is s square t mk square, this is s square m into m plus 1 into 2m plus 1 by 6, k into m plus 1, right? And this is k into m plus 1. These two terms are same terms, only the difference is this, right? So therefore, now what I am calculating, I am subtracting, I am subtracting s square and s square t, that is s square minus s square t from equation 4 and 5. mk square will get cancelled, km into m plus 1 will get cancelled, and the terms we have m into m plus 1 into 2m plus 1 by 6, this is one particular term which remains here, m into m plus 1 into 2m plus 1 divided by 6, minus here the term which remains here, m into m plus 1 whole square by 4, m into m plus 1 whole square by 4. So these are the two terms which remains here. Hence, by calculating s square minus s square t, by simply taking LCM and all, you will get the term here m into m square minus 1 by 12. So it is getting lengthy, so I am not solving this and I am not doing this, and just if you solve this by taking LCM 6 4s are 6 and 4, the 12 is LCM, and so that you simplify this and you will get m into m square minus 1 by 12, right? So therefore, the difference between s square and s square t is m into m square minus 1 by 12. That is the change in the sum of the squares without ties, that is s square, with ties, that is s square t, it is m into m square minus 1 by 12. This is the quantity with positive sign. So therefore, this is the quantity is going to be reduced. Positive signs in the sense that s square minus s square t. If you subtract untied ranks, some of the squares of untied ranks and some of the squares of the tied ranks, the quantity is m into m square minus 1 by 12. Hence, this is the quantity is going to be reduced. The change occurs in the sum of the squares. Remember, just we have calculated only the sum of the squares, the term of the sum of the squares, which will be affected the variance. So therefore, this is what the quantity is going to be reduced. The change, effect of the change of the sum of the squares with tied ranks. If you have a tied ranks, then this quantity is going to be reduced. This quantity is going to be reduced. That is m into m square minus 1 by 12. You see that, for example, the three numbers are tied. Three individuals are tied. 3 into 3 square minus 1 by 12. How much? 3 into 3 square minus 1. 9 minus 1, 8. 3 into 8 divided by 12. Hence it is 4 2s, 4 3s, and 3 will get cancelled. Hence it is 2. Of course, simply 8 3s are 24. 12 2s are 24. So 2 is the quantity reduced. Exactly, I have explained the one particular example. One example I have given. for sum of the squares of the ranks. You see here, sum of the squares of the ranks 1, 2, 3, sum of the squares of the ranks 2, 2, 2, without ties, with ties. Sum of the squares here 14, sum of the squares here 12. How much quantity is reduced? 2. That's exactly we got here through the formula 3 into 3 square minus 1 by 12, that is equal to 2. Clear? So this is what the quantity is going to be reduced. For example, are such sets are there in X series? In X series, for example, are such sets. For example, this is the one set tied, another set. For example, 3 sets are there. R is equal to 3. Then what you have to do? M into m square minus 1 by 12 plus m into m square minus 1 by 12 plus m into m square minus 1 by 12. 3 times you have to add. The m will be different. M may be 3, m may be 2, m may be 4. Okay, 2 students may got tied, 3 students may got tied, 4 students may got tied, like that. So that is the reason why, for example, if you have R such sets in X series, then I am considering Tx, the change, the adjustment, or simply we call the adjustment. The adjustment in the sum of the squares is nothing but Tx is equal to 1 by 12, I am taking common outside, summation I is equal to 1 to R, mi into mi square minus 1 divided by 12 I am taking here. So this is what the adjustment in the X series. So m1 into m1 square minus 1 by 12 plus m2 into m2 square minus 1 by 12 plus m3 into m3 square minus 1 by 12, like that. You have to consider R set series. For example, similarly, in Y series, for example, S such sets are there. Yes, that is J is equal to 1, 2 and so on. Yes, here I is equal to 1, 2 and so on R. Then adjustment in the sum of the squares. You remember, adjustment in the sum of the squares is Ty. Let it be Ty. 1 by 12 into summation J is equal to 1 to S. Mj into Mj square minus 1 divided by 12. I have considered here. I have taken here. So these are the two particular formulas, Tx and Ty, in the adjustment in the sum of the squares, which we call adjustment in the sum of the squares, which means the change in the sum of the squares after tie occurs. If tie occurs, the change in the sum of the squares. With these values of the adjustments, in case of the tied ranks, the sum of the squares, now I am defining, that is I am deriving the sum of the squares, that is summation ui square new term. Summation ui square old term is n square, n into n square minus 1 by 12. So summation, this will be calculated by summation ui square minus Tx simply. Tx formula is this. So it is going to be subtracted. That I proved very clearly. Before that, some of the ranks tied ranks is 14. After that, it is 12. 14 minus 12 is 2. The quantity 2 is going to be reduced. That is the reason by minus Tx. Clear? Summation ui square minus Tx. So therefore, it is nothing but n into n square minus 1 by 12 minus Tx. Similarly, summation vi square new, sum of the squares